See, yesterday I gave you some formulas also. If you look at the Slack, just after the Bell-Coleman cycle, I have given you the formulas. I'm just sharing this Slack screen. Can you see the Slack screen? So there, correct. So those are actually we already discussed yesterday, but I just want to summarize the formulas here. So Bell-Coleman cycle, see, basically in refrigeration cycles, what is the difference between air cycles and refrigeration cycles? Air cycles already we discussed, right? This auto cycle, diesel cycle, all these things. So air cycles are meant for engines generally, and like in order to run the vehicles or heat engines. Whereas refrigeration cycles, they are meant for running the refrigerator, mainly refrigerating spaces, maintaining the cooling effect person. So both are for different purpose. So that is why when you come to air cycles, there is a term called efficiency. But in case of refrigeration cycles, it is COP. It's called coefficient of performance. Yeah. In case of refrigerations, it will be COP instead of efficiency. We talk about COP anamata, coefficient of performance. So that's why in the Bell-Coleman cycle also I have given you these formulas how to calculate the COP of a Bell-Coleman refrigeration cycle, right? So COP is nothing but the basic formula for COP is net refrigerating effect RE divided by work done. So basically refrigerating effect by net work done. Okay. సో రిఫ్రిజిరేటింగ్ ఎఫెక్ట్ అంటే మనకు ఒక రూమ్ లో ఒక కండిషన్ స్పేస్ అని చెప్పాను కదా ఇంతకు ముందు ఎయిర్ రిఫ్రిజిరేటెడ్ స్పేస్ ఉంది అనుకో లైక్ దిస్ Bell-Coleman cycle is used for maintain in the ships. They have a huge space in the ship where they keep the meat and other stuff. So in order to maintain the freshness of those food items, they have to maintain the space at a particular temperature. So that's why this Bell-Coleman cycle is used to maintain the cooling effect in that refrigerating space of the ships. So that effect and how much tons of refrigeration effect it is creating. Generally, refrigerating effect is measured in tons. If you see your house also, like when you buy a refrigerator or air conditioner, it will be specified in tons, correct? 1.2 tons, like that. So 165 liters, like so. Basically, here that is the refrigerating effect. In tons, you can convert that into kilojoules. That's not a problem because there is a formula to convert. 1 ton is equal to 3.5 kilojoules per minute, something. So we'll that is a formula. So refrigerating effect is the cooling effect divided by work net. That means in order to generate this refrigerating effect, how much of work we are used, that refrigerating system is using, correct? So that is net work. So how much motor it is taking, like I have given the formula in the above. What is the work net formula? Work net is equal to, just above 3 lines you can see, work net is equal to work of the compressor, work of the compressor minus work of the expander. So yesterday I showed you the diagram of Bell-Coleman cycle, right? So there we have two things running. One is compressor, another one is the expander. So compressor is basically used to compress the refrigerant, and this one expander is basically after expansion the work generated. So here work compressor is means compressor work is we are giving the external work to the compressor. whereas expander means it is coming from the system. That's why the net work will be the difference of these two, the compressor work minus expander work. So that is the net work. So that is the formula for that is Cp into T2 minus T1 minus Cp into T3 minus T4. So that also can be summarized like below, Cp, that Wn formula. So similarly, refrigerating effect formula also is there, Cp into T1 minus T4. So now if I substitute these two things in the COP formula, COP is equal to RE by Wn. So I will get the COP formula in terms of temperatures. So yeah, exactly. So there, same way you can also represent COP formula in this fashion also, another like 1 by Rp to the power of C minus 1. So where Rp is the pressure ratio, and C is that, yeah, that is gamma actually, gamma minus. So these are the formulas for calculating the COP. In fact, we already used these formulas in the above Bell-Coleman cycle formula. If you see yesterday, I'm just sharing you, just see the screen. So all these formulas I have used already. Just go through this problem, you will understand. So that is about Bell-Coleman cycle. So now today we'll go to another cycle called a vapor compression cycle. Okay. Yeah. So basically the difference between Bell-Coleman and vapor compression is, in Bell-Coleman we use air as working fluid. But when it comes to vapor compression refrigeration system, so vapor compression is using an external refrigerant as a medium. Okay. So, the working fluid will be something like ammonia or freon. These are the like metal. So those are the things uh, which are called refrigerants. I will send you the list separately. So using those refrigerants, we run this vapor compression refrigeration system. So, and that is one important thing about vapor compression cycle. Second important thing is, as you can see the title itself says that it is vapor compression refrigeration cycle. That means here the refrigerant is in the form of vapor. The refrigerant, suppose if you are using ammonia as a refrigerant, the ammonia vapor will be compressed. That means vapor compression means the ammonia vapor, it will be compressed in this refrigeration cycle. Instead of air, vapor will be compressed. Okay. So throughout the system, we are using vapor, ammonia, or whatever refrigerant we are using, that will be circulating throughout the system. So in order to explain the vapor compression system, I have used these two diagrams here. You can see the diagrams. So that is, one is a TS diagram. Yeah. So TS diagram. Another one is a pH diagram, pressure enthalpy diagram. Okay. So I will first pressure enthalpy diagram. pH. So before going to that, I'll first show you the outline diagram of this vapor compression cycle. Okay. So outline diagram is what are the important components in this system and how they are connected. So here you can see that there is a compressor. 1 to 2 is a compressor. In between 1 and 2 there is a compressor. That means something is coming into the compressor and it is getting compressed and sending out. So that something is nothing but a vapor form of ammonia or vapor form of refrigerant. Any refrigerant we are using, generally ammonia. So vapor comes into the compressor and it gets compressed. And obviously when you compress, the high temperature and pressure both will increase for the vapor. Then it will be sent to this condenser. Here you have a condenser. So between point 2 and 3, that is condenser. Okay. So condenser means obviously it is going to reject some heat. So that means whatever hot vapor ammonia is there, it is going to release some heat to the atmosphere. Thereby, ammonia vapor will become liquid ammonia. Because when you remove the heat from the vapor, so obviously it will change the form to liquid. So that way, after the condenser, what you will see is a liquid ammonia. Yeah, so that liquid ammonia will be sent to the expansion valve. Okay, so in the expansion valve, you are going to have this the liquid ammonia will be suddenly expanded. Okay, when the valve opens, it suddenly expands and it causes it will become the temperature will be very less. The temperature will reduce, pressure also will reduce. So that is what happening in the expansion valve. Once it is coming out of the expansion valve, it will become very cool liquid, the refrigerant. So it will be very low temperature liquid ammonia, which will be sent to the evaporator. Okay. So in the evaporator, obviously when the ammonia liquid at a very low temperature is entering, what it will try is, the evaporator is nothing but it is a place where the refrigerating effect is taking place. Okay. అంటే మనం ఏవైతే స్పేస్, సపోజ్ I told you, right, is the refrigerator, the evaporator chamber, that is where we keep all these substances like food items, whatever, juices, everything we keep there. That is nothing but the evaporator chamber. Okay. So evaporator chamber, surrounding this evaporator chamber, this cool ammonia liquid will be circulating. So what happens is that that cool liquid ammonia will try to absorb the heat from the food substances. Like, so it will absorb the heat from the apples or juices, whatever. So thereby those substances will become very cool because they are losing the heat. They are losing the heat. Where that heat is going, that heat is going to the refrigerant liquid. So obviously the refrigerant liquid will become, starts boiling. So the refrigerant liquid becomes vapor, and inside the evaporator, the temperature will be very low because of this cooling effect. So that is how the food items will be maintained as a fresh. That's number one. And the temperature of evaporator will be very low, sometimes even minus also. Okay. So at the end of the evaporation process, like 4 to after the evaporator, the refrigerant form will be now vapor form because it has absorbed the heat from the food substances. So it becomes vapor. So that vapor ammonia or vapor refrigerant, it will be sent to the compressor once again. So that is how the compressor is getting vapor form of refrigerant, right? So that is a complete cycle. That means again the compressor will compress the vapor refrigerant, and that compressed refrigerant will be sent to the condenser. So like that the cycle goes on. So this is the complete like cycle of this vapor compression refrigeration cycle. Okay, this is a flow. Now we have to examine what are the processes involved. I mean, what are the thermodynamic processes happening in this vapor compression cycle. That is, here I have given 4 processes, right, just above this diagram. So you can see process 1 to 2 is a isentropic compression process, and process 2 to 3, yeah, so that is in the condenser, that is happening in the condenser. Now isoenthalpy. So that is happening in which place? Correct. So that's what I said. Expansion valve is also called throttle valve. So it is iso expansion process. That means iso enthalpy process means enthalpy will remain constant in this throttling process. Enthalpy will remain constant. So that is called throttling process, which I explained you in the beginning of this unit 1. We have discussed what are the different processes. So there is a process called isoenthalpy process also. That is also called throttling process. So in throttling process, what happens is the enthalpy remains constant. That means H3 will be equal to H4. Before and after the throttling valve, the enthalpy will remain same. So that is the 3 to 4 process, isoenthalpy. Now, after that, what is the process we have? 4 to 1. Yeah. So that is happening in which component? Correct. So it is in the evaporator. So these are the processes it is following. So we have one isentropic compression, then constant pressure heat rejection, then isenthalpic expansion, then constant pressure heat absorption, right? So all these processes I have shown here in the TS diagram. So here you can see 1 to 2 is compression, and compression, once compression happens, obviously the temperature will increase, right? So T2 will be very high. From there 2 to 3 is the condensation process. So that means it will start solid, it will start becoming liquid. So you can see this dry saturated curve. We already discussed this in the third unit, dry saturation curve. So anything above this dry saturation curve is the superheating zone. So point number 2 will be in the superheated zone. That's what happens, right? When the compressor is compressing the liquid vapor refrigerant, the temperature will shoot up like anything, and the vapor becomes superheated vapor. Okay, so that is how this point 2 is falling in the superheated zone. Okay, now from that point 2, it is being condensed in the condenser. So 2 to 3 is a condensation process. It is a constant pressure heat rejection. So that's why the temperature will become very low. At the same time, the form of the substance will become liquid. So that's why you can see that point number 3 is falling on the liquid line. The curve, left hand side of the curve is a liquid line, like I told you. So it is on the liquid line, liquid saturated line. So that is the point number 3. And you can see that 2 to 3 is the heat rejection is happening. And then 3 to 4 is what? Expansion valve. That is isoenthalpic process. So you can, if you see the pH diagram here, pH diagram, P means pressure, H means enthalpy. So you can see that 3 to 4 is a vertical line. That means in the pH diagram, look at the pH diagram. So 3 to 4 is the vertical line, which means enthalpy is constant. So that's why it is a vertical line. So you have to see both the diagrams. So then we have 3 to 4 as a isoenthalpic process, and then 4 to 1 is a constant pressure heat rejection. Yeah, sorry, heat absorption. That means in the evaporator, it is absorbing the heat from the substances, right? So you can see that in the pH diagram, process 4 to 1 is a horizontal line, that is constant pressure line, right? So that's why 4 to 1 is a constant pressure heat absorption process. It is happening in the evaporator. So once you understand these two diagrams, right, the TS diagram and the pH diagram, then it is pretty much easy to solve these problems, solve the problems of this, what do you call, the vapor compression refrigeration cycle problems. Okay. So at the same time, I'll also share you one more diagram. So that is uh, just to explain in the examination how to, what is the vapor compression cycle, to if you want to explain it better, so I have another diagram which I will share you. So this is the diagram, like same whatever line diagram I showed you to explain the vapor cycle. So they have put the components here, compressor. You are able to see that diagram. What diagram it is? Compressor. What all you are able to see? Which components? Ah, yeah, correct. So, ah, so mainly main important components are compressor. After compressor, that pipe is the condenser. Then there is a receiver. Then there is a expansion valve, to, and then expansion valve. After expansion valve, the big top big that pipes is evaporator. Evaporator. So from evaporator again it comes to the compressor. So this is the same diagram which I explained as a line diagram before, and here in this I have there is explanation about what is each component, like compressor, receiver, expansion valve, evaporator, what they do. They have given. So I'm going to share you this diagram. So just go through this also. Just a minute. So sometimes in an examination they will ask draw a neat sketch of vapor compression cycle and explain the components like that. So you can uh, you can explain this. Okay, so most of the time they ask problems, but sometimes if they ask a theory, you have to write like this. Okay, so that is the uh, all about vapor compression refrigeration cycle. Huh. Okay, nice. So what I'm going to do now is I will give you some brief idea about COP of a refrigerant. Okay, so what is COP of a vapor compression refrigeration cycle? Okay, so what is COP? Already I explained you in the Bell-Coleman cycle, right? COP is nothing but the refrigerating effect ratio of refrigerating effect to the work done, work net, right? So the COP definition remains same. COP, are you able to see that whiteboard? Uh, so COP is nothing but refrigerating effect, okay, divided by divided by the work net, correct? Work net. So that is a net work done. Net. Why we are calling net means the difference between compressor work and the expander work. So here also the compressor work, and um, there will be a small pump which will be running to circulate the fluid. So that the difference of those two will be the work done. But generally we neglect that here. We don't. We simply take the compressor work only in case of vapor compression cycle. So there is a formula. So that is, this is nothing but, see, this is nothing but, you have to write like this. What is the refrigerating effect is Q2. That means uh, Q2 is where it is happening. Yeah, I told you, right? Q2, Q1 in the diagram. Q2 is the heat absorbed in the evaporator, right? Divided by work done. So this is the formula. Okay. So where, uh, yeah, so where, I'll write it for you. Q2 and where Q2 is, one minute, where Q2 is the heat absorbed. Heat absorbed where? In evaporator, right? Okay. And uh, W W is W is W is work done by the compressor. Yeah, by the compressor. So like this, if you understand, then our job is very easy to calculate the COP. Okay. So what is the COP here? See, heat absorbed in the evaporator means that we have to take from the diagram. See, look at that same diagram once again, the TS diagram. Okay. So what is TS diagram saying is there is a process in which process the heat is absorbed in the process 4 to 1. You see the TS diagram. In the process 4 to 1, the heat is absorbed. So that means, yeah. So that means you can see the pH diagram also here. Process 4 to 1 is that's where the heat is being absorbed from the food substances. That means there is a change in enthalpy. Okay. So you can see that enthalpy at 0.4 and enthalpy at 0.1. Okay. So that means the difference of these enthalpies is nothing but the heat absorbed. The difference of these enthalpies is nothing but the heat absorbed. So I can say that the Q2 is nothing but H1. Okay, H1 is enthalpy at 0.1 minus H4, that is enthalpy at 0.4 from the TS diagram. Okay, so from TS diagram, Q2. Okay, so Q2 is equal to H1 minus H4, right? That is one thing. And also W is equal to H2 minus H1. Why? Because see, if you see the diagram once again, where the work we are spending the work in the compression process, right? That is process 1 to 2. So the compressor is taking some external work in order to compress the vapor refrigerant. So that external work is consumed in process 1 to 2. That means if you look in the pH diagram, the enthalpy diagram, right side, so whatever difference between point number 2 and point number 1, the enthalpy difference, that is nothing but the work done, work taken by the compressor. Okay. So that's why I have written here W is equal to H2 minus H1. Right? Clear, right? So now we defined what is Q2 and what is W. Okay. Now also we can say that H3 is equal to H4 equal to H4 ante enthalpy at point number 4 is equal to HF3. Okay. So H ante H ante enthalpy, but because it is a fluid, see, look at this enthalpy diagram once again. H4 equal to H3. You see this right side pressure enthalpy diagram. H3 to 4 is a vertical line. 3 to 4 is vertical line. That means it is a isoenthalpy process, right? So that means H3 will be equal to H4. So that's why I'm writing here. That's why I'm writing here the uh, that's why I'm writing here H4 equal to H3, right? see H4 is equal to H3, but I am writing F. Why? Because it is a fluid, it is on the fluid line. It is on the fluid line. So anything on the fluid line is uh, uh, it is F. We will indicate by F, right? So now coming back to the COP formula, Q2 is I am representing as H1 minus HF3. Okay, because Q2 is a so the therefore so Q2 is equal to H1 minus HF3. Okay, so so Q2 I am substituting in the COP. Similarly, W I am substituting H2 minus H1. Okay, so these are the formulas for calculating the COP. So if I know the enthalpies at different points, I can easily calculate the COP of a vapor compression refrigeration cycle. Okay, so that is about the vapor compression refrigeration cycle. So what we have to do, sometimes they will be asking questions, they will be asking problems. Okay, so problems they will give in such a way that the condition of vapor, based on the condition of vapor, you have to calculate the enthalpies. Okay, so for example, I'll tell you. See, go back to this diagram, enthalpy diagram. See, most of the times the condition of vapor after compression, it will be superheated condition, correct? So point number 2 is in a superheated condition, but sometimes it may be on the dry saturated line. That means if point number 2 will be on the dry saturated curve, on the right side curve. So at that time the formula will be H2 will be different. H2 will be at that time H2 will, you have to calculate enthalpies, no? So if it is a dry saturated, I explained you in the previous units, H2 H, if it is on the dry saturated line, H is equal to HF plus HG. Sorry, HF plus HFG. Right. So suppose if it is on the point number 2 is in the superheated zone, then enthalpy will be Hg plus Cp into T superheated minus Ts అనే ఒక ఫార్ములా ఉంది. H superheated కి ఒక ఫార్ములా వస్తుంది, Hg కి ఒక ఫార్ములా వస్తుంది, Hf suppose if it is in between means another formula will be. So depending upon where is the point exactly, so you have to apply that particular formula for calculating the enthalpy. Okay, so that is the fundamental thing you have to remember when you are solving the problems. Okay, okay, so I'll what I'll do, I'll share you quickly one problem which I have solved, vapor compression. Just give me 1 minute, I'll be back. One second. Because I want to complete one problem today, so that you can practice it in your free time. So I'm just sending you my problem. if you understand the principle, it is very easy to solve the problems. Okay. So far you have understood the right how the COP will be calculated and all that. Okay, just a minute. I'm telling you. So in case of refrigeration cycles, it will be COP. Okay, in case of engines, what will be the things you will be calculating in case of engines like air cycles? There it will be efficiency. There it will be efficiency. Here it will be COP. So I'm sending one problem. Vapor compression refrigeration cycle problem. Vapor compression. 1 minute. Actually, vapor compression refrigeration cycle. Actually, I'm using the Google speech this thing. I'm not talking to you actually. Vapor compression refrigeration cycle problem. Okay, so that is already sent in the Slack. Okay, 1 minute. Some problem in this. Okay. Yeah, now it is gone. Okay, so anyway, I'll send the problem in this Slack. Uh, 1 minute. Huh? Okay, so no problem. I'll send it once again later. Some issue is there here. Okay, I am sending in your WhatsApp itself. So later you can put it in the Slack. I will put it. So that is the type. That's a problem they will give. Generally, that is the type. That's how they will give the problem. So you have to calculate the refrigerating effect, and then your work done and COP. Actually, I'll put it in the Slack also. Some after that, after the class, I'll put it. So for now, you can go through this problem. So if you see the problem, how it is working is basically they will give the condition of the vapor. Okay. So look at I will share you the same thing on the our whiteboard. Just 1 minute. One second. Okay. Okay. So can you see that any problem in the uh, come back to the Zoom. Okay, Zoom, I have shared the same problem. Okay, so they will give the problem like this: find the theoretical COP for a CO2 machine working between 25 degrees to minus 5 degrees. Dryness fraction CO2 during suction stroke. Uh, that means before entering the compressor, the dryness fraction they have given. So, so you have a table form. So that is information like before and after the compression. So here, see 25 degrees is, see where the maximum temperature will be there, that is 25 degrees. Minus 5 is in the evaporator. So see, generally the lowest temperature will be in the evaporator. Okay. So they have given the information about liquid vapor latent heat also at those temperatures. So if you, I have solved this problem using this TS diagram. Okay, so I have drawn this cycle also. So A to B, the same I have explained to you the compression cycle, right, in the TS diagram. So TS diagram, A to B is compression, B to C is condensation, C to D is expansion, and D to A is the evaporation. Okay, so using the cycle, so మనం ఏంటంటే entropy at point E, I am just reading the solution here. So entropy at point A is equal to entropy at point B because it is a isentropic compression, right? So using that, we can find the X. X means uh, what is X? Yeah, X is right. So X we have found out. Then that is after compression, what is the dryness fraction? Okay. Then after that, there will be one more thing. That is 1 minute. So this is the second page. So 1 minute. Okay. So anyway, I have sent you. So what we have to do, just we have to find out the refrigeration effect. So you can find in this way also area by calculating the areas. Okay, areas, and then what is the refrigeration effect? Okay, this is one way. Okay, but don't worry much about this. Okay, I'll explain you in another way which is more relevant for you. This is advanced type. They will not ask like this. There is a different way to solve the problem. Okay, using steam tables and all. Okay. Hello. 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 Hello.